Hello, and welcome to this quick take on the incremental compile flow for Vivado implementation. In this quick take, we will cover a general update of incremental compile, the improved handling of physical optimization in the flow, and automatic incremental compile for projects. To recap, the incremental compile flow reuses placement and routing for unchanged portions of a design to improve compile time and preserve design closure. As shown in the flow diagram, a completed design run that meets or that is very close to meeting design goals is used as a reference design. The routed DCP of the reference design contains the placement and routing data. Next, the design is updated with changes, resulting in a slightly different netlist. Instead of placing and routing from scratch, the placement and routing data from the reference design is applied for matching netlist objects. Placement is reused for unchanged cells, and routing is reused for unchanged nets. Routing reuse occurs at the finest level possible so that even if a net changes slightly, for example if fanout loads are added or dropped, the maximum amount of routing is reused. The result is a design that is mostly placed, routed, and time enclosed, which is a much better starting point for the incremental placement and routing to close the remainder of the design. Now for a general update on incremental compile. As of the 2015.3 release, all 7 series and ultra-scale devices have full production level support. Based on extensive internal testing, the average compile time speedup is 2x, twice as fast, when design changes are limited to 10% or fewer of the total cells. The compile time speedup may exceed 2x when targeting larger designs and larger devices that typically have longer compile times, and when design changes are smaller than 10% of the total cells. Beginning with the 2015.3 release, the incremental compile flow has improved its handling of physical optimization usage. To understand the improvement, let's review how physical optimization is handled in previous releases. First, we'll take a look at how the original reference design is generated. Beginning with the synthesized netlist, logic optimization OpDesign runs and modifies the netlist to get the post-op netlist. Then the design is placed, which typically does not change the netlist, but results in the place and route data populated with placement data. Next, physical optimization is run, which typically modifies both the netlist and placement, which affects the place and route data. Finally, the design is routed, and the routing data is stored in the place and route data. The final routed reference DCP contains a netlist which contains changes from physical optimization. Next, the design is updated, and after OpDesign, the reference DCP is processed by the read checkpoint -incremental command, as illustrated in the green box. Here the place and route data is extracted from the reference design and applied to matching cells and nets in the revised design. There is a problem, however. The netlist of the reference design may be significantly modified by the physical optimization, for example, as a result of replication of high fanout net drivers. And this netlist is compared to the post-op design netlist, which is modified due to design changes, but does not include any physical optimizations. The result of this is that the netlist comparison yields a suboptimal match, and much place and route data from the reference design ends up being discarded. A common workaround is to use a post-placement reference design instead of post-route, but although that improves netlist matching, none of the routing data can be reused. The improvement in 2015.3 takes advantage of the new interactive physical optimization feature that can export physical optimizations as a tickle script of iPhysOp design commands. These commands apply the physical optimization netlist changes from the reference design to the matching cells and nets in the revised post-op netlist. Conceptually, this can be thought of as an incremental physical optimization step. Looking at the read checkpoint step again shown in the green box, the iPhysOp design tickle commands, which represent the physical optimizations in the reference design, are automatically extracted and applied or replayed to the revised post-op design netlist. The result is a closer match between the netlists because they both include netlist changes from physical optimization. Therefore, more place and route data can be reused, and the subsequent incremental placement and routing we'll have a much better starting point. Note that PhysOp design can still be used in the incremental run and will likely run faster with fewer new physical optimization opportunities. Also note any new physical optimizations will be captured so they can be applied the next incremental compile iteration. More importantly, there are no new steps required to use this feature. All detailed manipulations of the physical optimization data is hidden and automatic. Now we'll take a look at the automatic incremental compile flow for project-based designs. Prior to 2015.3, it's required to specify the exact location of the reference checkpoint for incremental compile as shown in the diagram. Then the netlist and place and route data are applied from that reference design to the revised design. Beginning with 2015.3, the automatic incremental compile feature automatically chooses the reference checkpoint to be used for the incremental compile run. Instead of copying the routed reference checkpoint to a known location for each iteration, simply enable automatic incremental compile and run implementation, and the reference checkpoints are automatically managed. This enables common schemes such as the one shown in the diagram, where the routed checkpoint from the current iteration becomes a reference checkpoint for the subsequent iteration. Automatic Incremental Compile is provided as a Tickle Store application as part of the Incremental Compile package of applications. The Tickle Store can be accessed directly from the Vivado IDE from the Tools menu. Then simply select and install Incremental Compile. Here are the Automatic Incremental Compile programs which are implemented as Tickle procs. The procs overlay the existing project infrastructure so that no extra steps are required besides enabling and disabling the flow. The procs are in the namespace of Xilinx Incr Compile. Enable Auto Incr Compile enables or turns on the incremental compile flow for the current run, and Disable Auto Incr Compile disables or turns off the flow. When enabling, there are different schemes for handling how the incremental checkpoints are managed in the flow, which we will cover in a moment. There are also two helpful utilities: Get Auto Incr Compile Selected Scheme, which returns the name of the automatic scheme, and Get Auto Incr Compile Selected Scheme Checkpoint, which returns location of the reference checkpoint based on the scheme. The latter is helpful for debugging and also for revision control, as a reference checkpoint is required as a source to be checked in and kept under revision control. Here are some examples of using Automatic Incremental Compile. Here we have a project with several runs, with Impulse 6 being the active run. We wish to run Impulse 6 using the incremental compile flow. We enable Automatic Incremental Compile using the proc Xilinx Incr Compile Enable Auto Incr Compile, and with the -last run option to choose the last run scheme, which means use the most recent compile run as a reference for the incremental compile run. In this project, Impulse 5 is the most recently completed run, so it will be used as the reference. To run the flow, we launch the implementation run, which can be as simple as clicking the Run Implementation button. Here are a few other quick examples. We mentioned earlier that Automatic Incremental Compile can be enabled with different schemes by specifying an option. Last run we already covered, which means use the latest routed DCP as a reference. The fixed scheme uses the routed DCP from a specific run by specifying the name of the design run. Best WNS and Best TNS choose the runs which have the best WNS and TNS respectively. To get the current scheme, use Get Auto Incr Compile Selected Scheme. For example, here it returns last run. To locate the reference checkpoint being used in the flow, run Get Auto Incr Compile Selected Scheme Checkpoint, and it will return the full path of the routed DCP file. As we mentioned before, this file can be added as a source file when placing design sources under revision control. So to summarize, the incremental compile flow is a robust, production quality feature that has been in use for many releases to improve compile times and preserve design closure. Expect a compile time speedup of 2x or even greater for large designs and design revisions affecting less than 10% of the total cells. for both 7 series and UltraScale. In 2015.3, the interactive physical optimization feature has been fully integrated into the flow, resulting in better quality of results when PhysOp design is used. Finally, a Tickle Store app provides an added boost for ease of use by automatically managing reference checkpoints. For further information, please check the following sources. The Vivado Quick Take on Incremental Compile Flow gives a good introduction and overview. UG 904, the user guide for implementation, contains a chapter devoted to the incremental compile feature. And UG 986, the implementation tutorial, includes a tutorial focused on using incremental compile after making a design change. Thank you for watching this Vivado Quick Take.
Thanks for viewing this quick take. If you found this video useful, you might be interested in taking some of our more in-depth training available at xilinx.com/training. We feature a variety of courses, both live and online, intended to make you proficient with Vivado and its features. We look forward to your participation. Thanks again for making Vivado successful.